Sounds great. So let's get started. So I'm going to talk about large-scale developmental EEG study today, as Sarah had alluded to. Before I begin, I wanted to acknowledge that all of the work that I'm going to speak about today has been done in collaboration with a close colleague of mine, Brandon Gibb, who is also at SUNY Binghamton. He ran this particular study called the Binghamton IDEA Project, which was funded by NIMH. And the study was primarily looking at social emotional processing in this particular age group. So this is middle to late childhood. However, everything that I will talk about today is about sort of intrinsic or resting state cortical activity in these same kids who were it was all part of the same visit. So when we're recording EEG, we're talking about population level activity of the cortex. We're talking about the synchronous activity of thousands to millions of cells. And we know that this activity at the population level exhibits spontaneous self-organization. In other words, even in the absence of any kind of a cognitive task or any kind of a sensory stimulus, the activity is actually organized in terms of large-scale networks. And although it was traditionally thought that this sort of resting state activity just represented noise, it now seems to be actually incredibly important for shaping responses to incoming stimuli and sort of constraining what kinds of cognitive processes can actually take shape on this sort of backbone of resting state activity. We also know that the microstructure, so to speak, of these resting electrical fields changes both in sort of healthy typical development, so it changes as a function of maturation, axonal pruning, myelination, things along those lines. It also changes as a function of learning experiences, both sort of Pavlovian conditioning and other forms of learning. And it also changes in disease, and we certainly know a lot about that. So we know about some of the alterations in resting state oscillations in diseases like schizophrenia and other neurodevelopmental disorders like autism. Hopefully you can hear me okay. I'm seeing some people are having some audio issues still. I will assume that everything's okay and proceed unless I hear otherwise. So the studies that I'm going to talk about today, we examine how this activity becomes reorganized, this sort of resting state rhythmic cortical activity becomes reorganized during this particular sort of period from early to late childhood. And this is a developmental period that has been somewhat neglected in the existing literature. So usually people will, to the extent that they have examined it, oftentimes these age bands will all be averaged together. And what we wanted to do here was to look at 1-year age bands in order to chart development, sort of fine-grained development of these cortical electrical fields during this sort of important developmental period. So it's all, as I said, endogenous cortical functional activity recorded during an eyes closed state. These were there were 33 cephalic electrodes that we recorded from, which is the montage that I'm showing you here. And the sample size included 1,000 healthy children, so no neurosensory impairment, neurodevelopmental disorders. And these children were recruited from the upstate New York region. The age ranges varied from 7 to 11 years of age. We also have extensive genomic and additional data like neighborhood crime statistics on these same children. So as I'll talk about in the future directions, some of the work that we're looking into now is trying to link the patterns that we have discovered to variation in the amount of crime that these kids have been exposed to as a function of their living situation and the places where they've been raised, other indicators of sort of paternal stress. Okay. So the first set of findings that I'm going to talk about is from a paper that we published in Neuroimage several years ago now. I'm going to start off just by talking about developmental changes in absolute spectral power. And rather than binning power into sort of a priori frequency bands, the approach that we took in this particular publication was much more data-driven. So we actually analyzed changes in EEG spectral power in 0.5 hertz bins without putting them into predefined bands like delta, theta, alpha, and beta, and so forth. And we used permutation statistics and Monte Carlo permutation statistics in particular in order to be able to sort of take more of, as I said, a day-driven, a-theoretical approach and really discover regions and particular frequency sort of areas where we would discover the strongest developmental changes. And let me just orient you. So these plots are statistical saliency plots. They're basically colored plots of t-test values. And the oldest kids, so the 11-year-olds, are compared to 7-year-olds here. 11-year-olds are compared to 10-year-olds here, 9-year-olds, and 8-year-olds. And anything that you're seeing sort of that is marked by these black borders are regions that survived statistical significance using this permutation testing approach. And hot colors basically indicate regions of the across electrodes as well as in the frequency space where the younger kids had more spectral power than the older kids. So what we find across age is that there are basically, as kids get older, there are reductions in these slow wave frequencies that sort of, roughly speaking, encompass traditional delta, theta, as well as what are traditionally called alpha 1 or lower alpha bands. So up to about 9 hertz or just on the border between 9 and 10 hertz. So that whole swath of sort of slow wave regions starts off being a lot of power in there in the youngest kids, and with each single year of development, there are progressive reductions in the amount of slow wave power. And that is sort of like region nonspecific, so it tends to sort of extend from the frontal regions of the head that are sort of organized at the top of the graphs, all the way to the central, posterior, and occipital regions. In addition to that, we find second region of sort of beta activity, so from about 15 hertz to about 30 hertz, so that's sort of traditional beta range, that also tends to decrease with age, and that tends to be distributed somewhat more across the sort of frontocentral areas. So it might be some sort of a motor beta band activity. And as these age groups get closer and closer together, so as you move from comparing 11-year-olds to 7-year-olds, 11-year-olds to 9-year-olds, 8-year-olds, 9-year-olds, 10-year-olds, the reductions get smaller and smaller, obviously. So it's a very sort of a linear decrease in slow band power. When we treat age continuously, so rather than putting it into one age bins, we also are finding sort of similar patterns, a negative correlation between the continuous age in years and the amount of slow wave power density. Slow wave power density here being the combined power from 0.5 hertz to 7 hertz. And again, this particular pattern tends to not be sort of specific to a particular region. We find that in occipital, parietal, central, and frontal regions across the board. In case you're wondering, it does not tend to be different for boys and girls. So the exact same linear fit is found for both sexes. So we didn't find any particular or any drastic sex differences in terms of this pattern, although there are some other minor sort of sex differences that are reported in the paper, but they're sort of probably not worth talking about in this talk. So in addition to absolute power, we can also look at what has been called relative spectral power. So what this is, for people who are not familiar with EEG, is simply you represent the amount of power in each 0.5 hertz bin as a fraction of the total power in the entire spectrum. And one of the nice things about relative spectral power is that it helps you to normalize for factors like skull thickness, cell density, cell packing, that are known to sort of influence absolute power. So you control for that, and when you look at relative spectral power, you can often come to slightly different conclusions than you would looking at absolute spectral power. And so here what we find, again, the orientation is the same. So these are, again, spectral saliency plots comparing 11-year-olds to the youngest kids here, 11-year-olds to 8-year-olds, 11-year-olds to 9 and 10-year-olds. And here, basically cool colors, so the color blue here is going to indicate regions where the older kids actually have more power in those regions relative to the younger kids. So in other words, what this is showing you is that older kids tend to have more, there's a redistribution of spectral power, relative spectral power towards the higher frequencies, starting about 10 hertz and then extending outwards from there. And that is most pronounced for when you're comparing the oldest to the youngest age group. It is still there, although more restricted specifically to what has been traditionally called the alpha 2 subband or the higher alpha subband. When you compare the 11-year-olds to 8-year-olds, and then with each subsequent age, those differences diminish until basically when you're comparing 11-year-olds to 10-year-olds, there's no differences in relative spectral power at that point. So in addition to that, we looked at another measure of electrocortical maturation, which has to do with where is the individual alpha frequency. So where does the alpha frequency peak for any given individual? So typically it tends to be around 10 hertz, which is what's being demonstrated here in the black thick line. That is the average of all 11-year-olds. But the other thing that you can see is here I've plotted individual 11-year-olds as light gray lines. And what you can tell is that there is a lot of individual variability here in terms of where a particular person's centroid or alpha centroid is, right? And so that would define their alpha peak frequency. There is good evidence that alpha peak frequency, maturation-wise, is sensitive to things like white matter density and axonal myelination. So this is sort of an additional interesting metric that we can track. And what we did was that we implemented an automatic peak detection algorithm that looked for, within each individual's EEG, looked for where their alpha peak was within this sort of window that's illustrated by the red rectangle. So roughly speaking, between about 7 hertz to 14 hertz. So we know the peak is somewhere in that range, and then the peak detection algorithm finds it uniquely for each individual. And what we found basically is that across age, the alpha peak systematically accelerates. So there, from 7-year-olds to 11-year-olds, there is actually about a 1 hertz slide in the alpha peak frequency. So the alpha peak frequency is oscillating at a faster rate for the oldest kids compared to the youngest kids. The error bars here, by the way, are 95% confidence intervals that we estimated using about 1,000 random bootstraps. So there are confidence intervals. So we find that the brain is, at least in the sort of posterior regions where alpha tends to be dominant, is oscillating at a faster frequency as the kids get older. We know that probably actually this peak continues to accelerate into late adolescence, most likely. And then it seems to start to decelerate old age and senescence, although we didn't have our particular sample was not well suited to address that particular question. Okay, so the next thing we looked at was the organization of cortical networks, so functional connectivity networks. So in addition to the changes in the EEG power spectrum that I just showed you, that we just spoke about, we wanted to look at how the sort of architecture, the topology of these networks changes from during this same developmental time period. Now, as many of you will know, inferring functional connectivity on the basis of scalp EEG is a tricky business, a controversial business. And the reason for that is that there is volume conduction, right? So you will have dipoles within the brain that will project to, through the cerebrospinal fluid. They will get smeared out by the skull and so forth. And the electrodes that are at the scalp will pick up what's called spurious connectivity. So they will pick up activity from the same neural dipole that may show up as highly synchronous activity, but it's actually not interesting, right? It's actually just telling you that there is massive volume conduction that's going on from a common dipole that's being projected to both of these scalp electrodes. So that is a major problem for being able to infer functional connectivity from scalp EEG. And the way in which we tried to address that was through using a particular measure of functional connectivity that is known as phase lag connectivity. And phase lag connectivity basically ignores any connections between two electrodes that have 0 millisecond phase lag. So it's sort of assuming that 0 millisecond phase lag is not real, that it's spurious. And that's controversial in its own right, but I'm not going to open up that can of worms. But the basic point is that this particular measure, which is called the imaginary part of complex coherency, is able to basically ignore these connections between adjoining electrodes that we think are maybe not so interesting and that they probably are artifactual. And instead, what this measure that we used is more sensitive to are these long-range patterns of connectivity. So between, for example, the frontal and the posterior sections of the brain, while ignoring these ones that we think are relatively trivial. So I hope that's clear. We can, if not, I'm happy to talk about it later. And due to computational demands, when you're computing functional connectivity from EEG, we actually had to bin connectivity bands into predefined frequency bands. So we looked at theta, alpha, and beta bands. And what we basically found when it came to functional connectivity was that the only one that was sensitive to developmental change was the alpha functional connectivity in the alpha band, which is what I'm plotting here. So here what we're plotting is the amount of power in the alpha band is basically what's being color-coded. And then we thresholded the connectivity values. So what I'm plotting here are connectivity values that exceeded the 95 sort of percentile of the distribution. And what you find is that alpha connectivity basically increases, right? It's like a tree that grows as the children are getting older, to the point where the 11-year-olds have a very highly integrated alpha connectivity network compared to the 7-year-olds and the 8-year-olds. And these changes seem to be somewhat more sort of nonlinear, right? So there's a drastic jump that seems to happen somewhere between 10 and 11 years of age. Now, the next thing we did was to also turn these connectivity networks into graphs and apply graph theory to them in order to derive some sort of quantitative summaries of the properties of these networks. And we use a weighted network approach where we did not have to binarize the network and apply some arbitrary threshold. We took the reciprocals of these connectivity weights or the connectivity strengths in order to do that. And I'm going to show you three graph theory metrics here: characteristic path length, network modularity, strength homogeneity. So characteristic path length is basically an index of how integrated the entire network is. And so the smaller this value, the more integrated the network. So as you move from 7 years of age to 11 years of age, the network becomes more integrated. Network modularity, you can think of it as a measure of how segregated the networks are. So basically the networks become less segregated. So they're more integrated, less segregated as you move from the younger to the older age groups. And strength homogeneity has to do with how evenly distributed the strengths of the nodes within the network are. So the lower this number is, the more spatially variable the functional connectivity networks are. And that is exactly what you find with age. So just to sort of recapitulate, as kids get older, their networks are more integrated, less segregated, and more spatially variable. And I'm going to talk about why we think that is interesting. Just really quickly, this sort of like increased integration, decreased segregation seems to parallel some similar findings from the fMRI modality. And I believe actually the speaker coming after me will be able to speak to this much better than I can. But basically, there is a trend that across the age span, as you look at children to young adults, these long-range networks in particular start to become more integrated, more heavily connected to each other. So that is perhaps a converging finding across multiple modalities. So just really quickly, interim summary. So we find evidence of large-scale reorganization of cortical electrical fields that takes place from early to late childhood. And this is characterized by reduced signal amplitudes and power and better integration. So these networks are becoming better tuned and they're better able to sort of synchronize with one another. And really quickly, I'm going to talk about how these changes may sort of impact the informational complexity that the EEG signals contain within them. Go through that right now. So we used a measure of brain signal variability as an estimate of what you can think of as neural complexity. All of those are loaded terms that are sort of controversial, but I'm not going to get into that now. Basically, sort of at a very high level, sample entropy quantifies how predictable a particular time series signal is, right? So the more unpredictable or the more irregular a time series signal, the greater is the entropy of that signal. And the particular measure that we used here is a measure called multi-scale sample entropy, which looks at the original time scale at which the EEG was sampled, and then also performs what's called a coarse graining operation, which is really a variation of downsampling. So you look at the amount of irregularity or sample entropy at fine timescales, and then you can also look at it increasingly coarse timescales. And the idea is that information is sort of distributed multiple scales of time, and that you need a metric that takes that into account in its quantification. So when you look at the multi-scale sample entropy of a regular repetitive signal, something uninteresting like a rhythmic sinusoid, you basically, at all time scales, it tends to be relatively sort of low, right? So it doesn't have it has a lot of regularity. It's not very unpredictable. You take white noise. White noise is very unpredictable at fine time scales, but actually the more that you coarse grain or downsample the white noise, the less interesting it becomes, because it basically averages to zero, right? So it contains less and less information at longer time scales. And EEG signals occupy sort of a middle ground where they sort of asymptote at some point at longer timescales. They act more like what's known as pink noise for people who are familiar with the sort of statistical properties of different kinds of colored noise. Okay, this is a typical sort of multi-sample entropy curve for an actual scalp EEG signal. So you might be wondering, is this measure completely redundant with spectral power, which what I talked about earlier? The question is, or the answer is that they're highly related, but they're not completely identical. And the reason is that multi-scale sample entropy is more sensitive to nonlinearities that are present in the brain signals than is spectral power, which is only sensitive to the linear properties of the brain signals. So here what we did was we took the original EEG time series in black, we took the phase of that signal and completely shuffled it, and then we did an inverse Fourier transform, put it back in the time domain in order to create a surrogate time series. And what you see is that if you take a traditional spectral power approach, you cannot differentiate the intact and the surrogate time series. They look completely identical. However, they are discriminated, or they do diverge when you do multi-scale entropy analysis at multiple time scales, and then at increasingly coarse time scales, they diverge even more. So this is just to sort of demonstrate that there is some unique information or unique variance that is being explained by these sample entropy measures relative to classical spectral power. So biological complexity, people think, is something about occupying this sweet middle zone between complete regularity and complete randomness. This is the way that people have thought about it. So if you take crystal lattice structure, that is the most regular thing you can think of, and it has very low complexity. It tends to be down here. If you take a container of gas molecules that are moving around randomly or stochastically, that is completely random, but also not interesting because it's essentially complete chaos. And it seems that brain signals and other biological systems occupy this sort of, like, as I said, sweet middle ground, almost like a Goldilocks zone, where it's a mixture of sort of complete order and disorder. And that seems to be very characteristic of biological signals. In the interest of time, since we lost some time, I'm going to skip over this. I just wanted to say that this measure is test-retest reliable. We believe that it has good psychometric properties. But I'm going to get right down to the age differences. Basically, what we find when, again, these are spectral saliency plots. Anything that is in green are regions that did not survive correction. They did not survive statistical significance. And these are organized into anatomical zones. So all the frontal sensors are at the top, central, posterior, occipital sensors. And hot colors here would indicate that the older kids have more, so to speak, complex brain signals, or they have more entropy in their brain signals across multiple time scales from fine to coarse. Okay, so that's the horizontal axis here. So the 7-year-olds have the least complex or the least variable activity, so to speak. Even compared to 8-year-olds to 7-year-olds, most of the differences between them tend to be sort of confined to electrodes that are covering the frontal and some of the central regions of the head. However, unlike spectral power, these differences are sort of less gradual. So, for example, when you compare 11-year-olds to 8-year-olds, there's basically very few differences in informational complexity of the EEG signal that are left. Those that are left, again, tend to be confined to some of the frontal regions. So there does seem to be this sort of like gradient. The development of complexity tends to move from the back of the head slowly towards the front of the head. The frontal areas are the last to mature, which again is not entirely surprising. If you split it up into finer age bands, so half-year age bands, there's very systematic changes. And the largest sort of jump in the informational complexity of the signal seems to happen from the group that is 7 to 7.5 years of age to 7.5 to 8 years of age. So that's the largest delta or the largest jump. And then as you break it up into subsequent sort of age subbands, the differences get smaller and smaller, to the point that we're not even plotting it here after 9 years of age. The differences are minimal. And again, this is just a distribution of average entropy on the head, just again indicating that there is that sort of posterior to anterior gradient in terms of its distribution. So I'm going to wrap up here. As I said earlier, we have evidence here that massive large-scale reorganization of cortical electrical fields takes place from early to late childhood. And what that consists of is reduced power, both absolute and relative spectral power, as well as better functional integration or tighter integration between distant regions. And what that means basically is that the brain signal, this sort of better functional integration, means that there is greater brain signal variability or complexity that scales up with age. And it basically indicates that the brain is able to bifurcate into more sort of unique states. So you have an expanded functional repertoire of resting state network states that we think really provides the foundation for the increasing cognitive and affective sophistication that happens during this particular age period. So what would be particularly interesting, unfortunately we didn't have that data, would be to have extensive cognitive information, IQ testing and other kinds of cognitive batteries on these same kids in order to be able to test this hypothesis that we can directly link this increased informational complexity of EEG signals to improve performance on a variety of tasks and reaction time, accuracy, things of that sort. So really quickly here, I'm going to actually end it there.